Welcome to today's lecture. We will be talking about energy methods. As this is a large field, we will restrict to an introduction to energy methods, more specifically. And you might ask, okay, why are they important for us? Or why are they important in this case? Well, let's look at these two cases I'm presenting right now. So on the left, I have a frame. You have worked with them with these cases where you have frames and you can see them on certain structures to support the roof more precisely. And on the bottom of the left side, we have a continuous beam that is called with several loads applied. And then on the right, you have these typical structures found when there are piping running through or over the ground. And they typically do these kind of shapes here because they need to adjust or be ready to absorb certain expansion and contraction due to the temperature of the pipe, basically because of the sun or night. So that temperature changes the length of certain parts of the pipe or on the pipe, and then they have to make these sort of buffers so the pipe won't break. Basically, that's the case for that. Also, you can find these type of structures when, unfortunately, they need to run pipes and they need to have an entrance to a certain place, or there's a road or something. So you can also find these type of structures here. Where energy methods kind of enter the scene in this case? Well, for the left case here, if you are going to apply forces and you wanted to know how that frame is going to deform, it is going to be complex to do it in the traditional way we have been doing it before. And when I call it traditional way, I'm not saying that energy methods are not traditional. When I say traditional, it's because it's something that you have seen already, and it's going to become very complex in that sense. Now, for this case, imagine that certain parts of these are stretching, and then you want to know how this is going to deform, even though in piping industry, there are standards that would allow you to calculate exactly how much this is going to deform. You would need a tool somehow to calculate those deformations in cases that are very complex, such as the frame, for example. Imagine that you have this type of frame, and then you have forces, force 1 or up to force n applied to it, and just you want to know how it is deformed due to these forces. And more importantly, of course, you don't have a software to do it for you, but you want to understand the whole process. So here is where energy methods play an important role in all of this. Now, what they are called energy methods, and there is something related to that. So let's say that whenever a body is deformed, or more specifically is strained, the energy is absorbed by the body. So meaning when you imagine that you have this beam here, and then you apply the loads, the beam is going to deform. And then if that deforms, then there's going to be some, as it is deforming, it is storing energy. Now, that stored energy, while the form is being deformed or being strained, is called strain energy. Yeah? So most typically you're going to find this topic on textbooks as energy methods, or strain energy, or total strain energy applications. So, but basically in a nutshell, whenever you deform something, there is an energy stored on that deformation. Think of it of a spring, for example. On a spring, when you compress or stretch the spring, there is certain energy stored on that spring, or in that spring, and then that energy is called strain energy, because it's an energy due to the straining of the element. Now, it is important to mention here that at some point, when we talk about strain, in comparison to deformation, strains can be very small in order, small in several orders than deformation. When we talk about strains, when we talk about deriving the equations for stress under certain circumstances, remember that we also consider that strain happens in a very small area, or happens in a very reduced way, meaning that it's not large in comparison with the dimension of the whole structure or element we are analyzing. Right? Then there is something that is specifically that if the strain is caused by the application of a load, then we need to take a look also on how loads are applied on these elements. For example, we can have 3 types of, speaking general way of applying these loads. For example, let me write it down here. So application of the load, because this is the load that is going to deform the element, the member, or the structure of the frame. So this load can be applied at least in 3 ways. So we can have, the first one is the gradual application of the load. Actually, now that I have defined like that, let me write it gradually applied. There it is, applied. It could be suddenly, like this, applied. Or it can become, or can be applied due to or via an impact. Awesome. Then depending on the case that we are going to have regarding how the load is applied, we're going to have different relationships or different consequences in the stored energy within the body. Yeah. Why it's called energy? Because it's something that is there, that if you remove the loadings, so that load can, let's say that element can give back that energy to any other thing. So that's why that energy methods deals with how is the stored energy within the bodies. Now that we have defined, okay, we can apply the loads, it can be gradually applied, it can be suddenly applied or impact. So let's define, before starting deriving these equations, three terms that are going to be important for you because you're going to be finding them in the textbooks and along if you go into the field of applying these energy methods in your work. So it is important that you know these terms that I'm going to mention here. The first one, important, let's call it important terms. Again, in here, important terms. And the first term we're going to have is resilience. You've heard this term maybe before applied to other contexts. Resilience, like this. And basically, resilience is what we have been talking about. So resilience is the total strain energy stored in the body. That's it. Let me write down below it is the, like this, is the total strain energy stored in the body. Now, resilience can be also defined as the capacity that a strained body has to do work if you remove the straining force, meaning that if we come to this place, to this beam, and then there is certain strain energy stored there, so it has certain resilience. So it means, what I mentioned, that if you remove the loading, then that stored energy, that resilience, is able to produce some work. And this definition is important because starting from the point of view of what is work, as a engineering definition or physical definition, what is work, then we're going to end up using this important relationship that says that work equals resilience or work equals the strain energy stored in the body. So again, resilience is the total energy stored in the body, but it's also defined as the capacity of a strained body to do certain work when you remove those straining forces. The second definition we're going to have is proof resilience. In here too, proof resilience. And proof resilience is the maximum strain energy that you can store in the body without permanently deforming the body. So if we take a look at the stress-strain relationship under Hooke's law, let me draw here this, we know already, so we have here strain, we have stress, and then we have our proportionality segment here, and then this changes to something like this until it breaks. So we know that at this point, if I cross this point here, then I jump into the region of plastic deformation. So here I'm going to put a line here. So this is going to be the segment or the sector of elastic, as we know, elastic deformation. And here we have the sector or the region for plastic deformation. So proof resilience is that total maximum strain energy that you can store in the body without permanently deforming it. So it means that proof resilience is the, how to call it, is the maximum strain energy, let me write it down here, that you can find here, you can find in the body. So max strain energy. When you stress the body, when I say stress, is that you apply forces and then you are going to reach a certain level of stress within the body, stress the body, right, up to the elastic limit, up to the elastic limit. That is called proof resilience, meaning you take it all the way up to here. So you go and stress it until stresses reaches the elastic limit, and then that is called, the energy that is stored there is called proof resilience. And then you have a third term that is good to know, that is called modulus of resilience. Like this. And the basic definition of what is the modulus of resilience is defined by a formula that says that the modulus of resilience is the proof resilience, like this, divided by the volume of the body, where V in here is the volume of the body. Great. Now, as mentioned in the term, when we're defining resilience, work in the end is going to be equal to the strain energy stored in the body. So we can define this like work equals to that strain energy. And we're going to define both terms using two letters. So we're going to use W for work, and then we're going to use U for strain energy. So this comes like this, and this comes like this. Perfect. Now to start defining one, then we need to define the other one. So for example, if we want to know about the strain energy, let's start working with work, because work is a better known concept for us during our studies up to today than strain energy. And work, as we know, is defined as the is a relation that exists between a force applied and the displacement that force causes. And you can see here that if we call deformation a displacement from certain point to another, for example, in this straight beam here, so if we pick up a point on a beam here on the top, and when you apply forces, that point is displaced to the bottom, to this part here, then you could say that those forces caused a work because they displace a certain part here, or let's say point there. In general, we could write this relationship as something like this. So I'm going to create again or draw again a Cartesian coordinate system. And when I am applying, let's say, forces here, I could call it F, and that's going to produce a extension or deformation here, like this, delta, sigma actually, it is. Then, just a second. Just searching for the value of this. So yeah, so we have delta, we have force here. Then if we know that the relation, or when I apply force, deformation is going to have certain, say, behavior here, so meaning that the relation that exists between the force and deformation, or extension or contraction, depending on the case, is something like this, then work is going to be defined as the integral from 0 up to the extent of the deformation of the force times delta deformation here. Perfect. So knowing this, now we can come back to these three cases and then try to understand what is the strain energy for a body when a load is applied under any of these three cases. Either the load is gradually applied, or is suddenly applied, or it is an impact. So let's go check that. So let's start with the first case as defined above, that is when the load is gradually, or is applied gradually. Now, when this happens, this chart here is going to acquire a very specific shape. I'm going to draw a similar chart as before in here. So we have here on one side, I'm going to write extension. I'm going to write down here load. And when you're applying this load gradually, what happens is that you start from 0, and then there is a 0 extension, and then you just grow with the load. The extension grows proportionally with the load. Something like this. So this might happen. Yeah? So it goes from 0, or from the origin, to this point here that we call M. So meaning that this here is, or this extent here is the load applied, we call it F, and this here is the extension applied, and we call it X, just to simplify things. So as work, as defined here, is the integral of this curve, which is equivalent to say that is the area of this under the curve, then, well, if this O to M is my curve, then the area under the curve is going to be represented by a triangle here. So meaning that all of this is going to be the work done, performed by this load that created this extension. Then the work here, around here, the work here, the work done, is going to be equal to force times displacement, which is the integral under the area, basically. And for this case, the work done is going to be 1/2 of F times X, because it's pretty simple when we know that. And then let's start just solving this case, because this is one of the first we need to define here. Now, at the end, we know that this is the, say, this is going to be the strain energy stored in the body. But let's put it in terms of other terms that we like to use. For example, we like to put it in terms of the volume, because we have talked about modulus of resilience. Let's put it in terms of stress, because at some point for us it's more interesting to see how much stress is developed instead of forces, because stress is the one parameter that is going to allow me to compare to something else in terms of rupture, for example, or plastic deformation. And also stress is going to tell me what is the proof resilience of this case, or how to calculate it, because proof resilience, remember, is the maximum strain energy you can store in the body. Well, basically is when you stress the body up to the elastic limit. So let's work it out so we can get to define strain energy in terms of those other terms. Let's see, we know that force, here, force, in terms of stress, equals to sigma, the stress, times the area. So this is a basic definition of stress in that sense. But as we're talking about strain, let's remember that strain also, strain like this, is basically how much that displacement, or how much it was displaced or deformed with respect or compared to its original length. So if we call that extension, and actually this should be a little bit like this, there. So if we call that extension is you have an undeformed object, body, then you apply forces, and then it goes to the deformed configuration. Then that deformation is the extension. So when you compare that extension with respect to the length, original length, that's going to give you the strength. Now, definitely we're simplifying the case here because that might work, for example, for certain linear deformations. Yeah. So, but it fits the case is also valid, and you're going to see that it's going to also be valid for other, let's say, scenarios. Now, from here, I can say that, well, I know then that x equals to what? To the strain times the length, or the length of the body. Perfect. Now, if I factor these two findings, F and X, back into the equation of work, I'm going to have something like this. So I'm going to have the work equals to 1/2 of the force, which is stress times the area. Then times what? Well, times strain times L. But also here, so strain is related to strength by what? So I know that strain equals to stress divided by the Young modulus, because this comes from the proportionality curve that I showed before. So now if I factor this in, meaning that I can factor this in here, and then both of these cases come back here, and this one come back, in here, then I could write that this is equal to what? To sigma divided by E, Young modulus times L. Then let me rearrange some terms, because this is going to end up being that work equals to what? To 1/2 of what we have here, sigma squared divided by E, Young modulus, then times A and L. But who is A and L? And this is something that why in the definition of modulus of resilience appears. So why do we care about the volume? Because the volume is here, let's say, embedded in this definition like this. So I could say then that the strain energy, because we know that omega equals U, equals to what? Well, to 1/2 of stress divided by the modulus times the volume. And this is the equation for the energy stored in the body. Okay, energy stored in the body, like this. You just write complete store in the body when the load is applied gradually. Then, as an exercise, we can say, okay, but now you defined these terms here. So we found the resilience. So what's the proof resilience and what's the modulus of resilience? And let's do it for this case, but the methodology is going to be the same for the other two cases where the load is suddenly applied or where there is an impact. So let's do it here. So what is the proof resilience? Well, that's simple. That's simple. Proof resilience, like this. So basically, you need to stress the body up to the elastic limit, meaning that the stress has to be equal to the yield strength of the material. Then proof resilience here is going to be equal to 1/2 of the yield strength of the material times the volume. And what this means is that the maximum strain energy that you can have in a body is tightly related to the yield strength of the body, of the material you're using in that body. That's it. So these are still very simple concepts, but these concepts are going to build up to become a powerful theorem in the end, one of many in the topic of energy methods that are going to help us solve for the deformation of structures such like these or even more complex ones. Resilience. Yes, now the final one is modulus of resilience, and let's do it here at the side, like this. And that's simply dividing the modulus of resilience. It's going to be equal to what? To, as defined here, is a proof resilience divided by the energy of the body. Sorry, by the volume of the body. So how much is going to be then? Well, is this term here, the proof resilience. Basically, if I divide this by the volume, then this is going to be equal to this. And this doesn't look good. Let me move it a little bit up like this. Yes. Perfect. Energy stored in the body, proof resilience, and modulus of resilience. Let's go now to the second case where the load is suddenly applied. And let's find out what's the value just for the energy stored in the body, meaning what's the strain energy of it. And let's compare how they look in front of this or it looks in front of this relation we found here for the case when the load is applied gradually. All right, let's do it. Now, let's start again with a diagram. So how would be a case where the load is suddenly applied? Yeah, so it's going to be something like this. So I should right here, I put it in green, so load is like this, is suddenly applied. Like this. So in that case, when we have such scenario, yeah, that's okay, maybe a little bit like this, then I have again the force, I have again here the extension or load, extension. So when that load is suddenly applied for the body, is kind of, it's just like this is going to happen, or the extension. So you have a load that is going to be felt like a constant load applied to it. It's not a load that is going to be increasing, but it's a load that is being felt like it's always been there, but the extension is going to develop due to that sort of constant load. So in this case, we're going to have again here the force apply here, and we're going to have here how much is extended due to the force. And again, we know that for the work done is the area under the curve. And what is my curve? Well, it's all of this, like this, up to here. Yes. For this case, we know that the work done by the load in a suddenly applied load case for this is going to be equal to the force times the extension. Now, we also know that the energy stored in the body is going to be equal to this case here. So this is a relationship that appears here. So, well, if these two things are equal, because they need to be equal for the case of energy stored or storage, let's say like that, then I can say that, let me rewrite that something like, well, F times X, but I know that X, it can be represented like this one here. So what is it? X can be represented like sigma divided by epsilon times L. So I could say that if the work equals this energy here, or stored energy there, that is written there, so this is going to be equal to F times, well, not even F. Now we can change everything. No, let's leave F at this point. F times X, but X is sigma epsilon times L equal to this term here, m squared divided by E times B. Hey, but B can be represented like area divided multiplied by L. Yeah? So I can cancel out a few things. I can cancel out, for example, L. I can cancel out this one here. I can cancel out this one and this one here. So this means that if I solve for sigma, solving for sigma, or the stress, then stress is going to be equal to what? Well, it's going to be 2 times F divided by A, which means that when you apply the load suddenly, then the stress induced in the body is the double as if it were applied gradually. So that's what this is saying in here. Great. Now let's go with the third case, the impact case. Like this. So let me try to represent in a schematic or a figure what an impact case would be. So let me draw a few shapes here. So I'm going to have a in here like this. Then I'm going to have another shape like this. And so another shape like, how to represent it. Let me move this a little bit up, like in here. Let this be the shape. Let me copy this one here, and I will move it up. And I will have another shape that will come from, let me just delete this one, or I could modify it like this, and then extend it like this. I'll just put a little bit longer here. And I'm going to have, or I'm going to say that all of this is fixed at the top. And what else? Well, we could say that, let me start deleting some or erasing some stuff, reduce this to this. So for example, I could say that, for example, this one in blue is a sliding mass, so it's prone to fall down if you release it. So it can slide on this shaft, let's call it shaft. And here, so what I'm going to say is that, well, this is a T-shaped body, like this. And this is a load. let's call it, to give it a proper name, this is a vertical rod. So this part here, I'm going to release, well, this rod is located at a distance h from this part here, and this part here, I'm going to call it collar. So of course, when I release the load, it's going to fall down, it's going to hit the collar, and this is what I wanted to do. And then due to the impact, then this is going to extend. Just exaggerating that, this collar extended, or due to the impact of the load, it just kind of extended to that much there. So move this. So it extended a certain amount from here to here, called like this. Like this, then being this distance from here to here, called L, or the original, or extended certain longitude. So this is the original length of the rod, and then when this load impacted the collar, then it extended this much here. Actually, it would be nice if I just move all of these to this part here. Yes, and then I can draw this part here, this line. So then let's see how is the stored energy, in this case, strain energy in this case. So let's bring a few relationships that we know. So we know that strain, we already said it, equals to stress divided by your modulus, so according to the proportionality, because we're working within the proportionality limits. But also strain can be defined using these two terms here. Because I could say that strain equals to what? Well, to the deformation divided by the original length. Then if I have this here, I could say that, like this, and like this, that, substituting one in another, that the deformation I got from the impact depends on the stress, the original length, and the Young modulus. So we know this relation, actually. You have seen it before. So, but then what's the work done by the load? Write down work done by the load. Well, in this case, this is the load, and work is force times displacement. So this load displaced from this position here up to this position here. So if I mark it from here, the load displaced from here all the way down to here, like this. So then the work is going to be defined as the load times the displacement of the load, or caused by the load, and that is going to be h plus this small extension here. Again, if I know that let's say the strain energy stored by the body is shaped like this, and let me write it down here. So it's 1/2 of stress squared divided by Young modulus times V, which we have seen that it could be written as this one here, E times AL. Then I could say that this one here equals this one here. So I could say that F times, well, the sum of length equals to this one here. So this is going to be nice, have a nice result like this. Awesome. Now, but who is this small piece here? So how much is the value? Well, we know that that value here is this one here. So it means that I could change these equations and say, well, but you know what? This one here, or the force, or the work done by the force, could be represented in terms of stress here. And this equals to, let me write down like this, 2EAL length. Then I can start working with this portion that we have just written here to find out something similar to this, because in the end, the excuse we used to reuse the stored energy in the body was to find out certain stress relationships that we could use, again, to compare to certain things like the strength of the material, or to see if that's going to comply to certain levels there. So if I start working with this part, with this that I have just written down here, then I could say, well, I can split up this parenthesis here, so I could say that FH plus F sigma L divided by E, well, is going to be equal to this one here, to your modulus AL. Yeah. And then I could say, let me put together, because I have this stress here, and as stress is my interest here to know what's the level of stress here. So let me put stress on one side, or everything on one side of the equation. Like, I have this one here, to E, A times the length, minus, F, L divided by E times stress minus FH is going to be equal to 0. Yeah. Now, if I multiply this times 2E, these terms are appearing here, AL. So it means that I can write this equation in the form of, if I multiply this times this, I'm going to have freed this element here, but when I multiply this element times this, so E is going to be cancelled out, L is going to be cancelled out, so the only thing that's going to be remaining are 2 divided by A, F, and this one here, so I could write it out as F L divided by E stress minus, let me see, I'm missing a 2 here, a 2, let me just copy this a little bit like this, 2, no, I said that this happened when I don't write it completely, so this one is going to be cancelled out, so let me just, this one, L and E, okay, now I have better guidance. So I have 2F divided by A, right? See? Yeah. Yes. And what else? This multiplies this, and then this one here. So I have FH, and FH is going to multiply all of these. So this one here, 2E divided by AL. It's going to be equal to 0. Great. Now that I have this, let me mark it, I can solve for stress to see how much is that. So let me try to do it. Let me see if I can do it at some point in here. So let me just quickly do it, and then just looking at solver, I haven't prepared it for that, but then the answer of this is going to be, I have a quadratic function, and that quadratic function is going to give me 2 answers, and one of the answers is going to be, well, the highest one is going to be this one here, P divided by A, that multiplies 1 plus this one here. You can use Python or any other tool to solve for this equation, 2A E H P divided by L, like this. Awesome. And let me mark down this equation. So let's analyze a little bit this last equation here that I got. So there are 2 interesting situations happening here. So in the first one, if the extension due to the impact is very, very small, let me write it down here. So 1, if this extension is very, very small compared to the height where the load was dropped, then the work is going to be what? Well, it's just P times H. So let me keep using P. Why I keep using P? It's just a constant to use. This is F times H. Then if that's the situation, when I equate the work equal to the relation that I found for the stored strain energy, so this is going to be that FH equals to sigma squared, this one that I have here, to EAL, which means that sigma squared is going to be equal, again, if I just solve for sigma squared, it's going to be 2EFH divided by AL, which is the volume, but let's keep it AL. But then that sigma, again, I can take roots here, and it's going to be this. So compare this to this. So in this case, this term is appearing here. So definitely it makes a difference to consider if you should take into account this condition, that how much larger is the height with respect to the extension, because that's going to give you, let's say, a great amount of simplification of the problem here. But this term, as you see here, is a term that is somehow appearing, well, it's not directly appearing here, but you can see the difference that exists between those 2 stresses, and it really looks like definitely if you have a considerable extension due to the impact, then the stresses are going to be larger. It would be nice to make an example, to have an example showing how different they are. But the second case would be that we could look at, we call this 1 and this one 2, is that, so what about if H is equal to 0? Well, if H is equal to 0, so I can take this equation that I have found right here, substitute H in here, which is going to make me, at some point this is 0, and then it's going to let me, or it's going to end up being that sigma equals to F divided by A times 1 plus square root of 1 plus 0, because H is 0. And in the end, sigma equals 2. Let's say this is going to be 2 plus this one here. This is interesting. So it means that So depending on the the magnitudes of the loads I'm using or considering for my examples, so this gives a good definition on how or what are suddenly applied loads or gradually applied loads. So it would be interesting in the future to factor in some time variable to more explicitly say what is a gradually applied load and what is a suddenly applied load. So, but in this case, it is a matter of just imposing the condition on the system, saying, okay, you know what, I'm working with a case where the load is going to be gradually applied or so on. Okay, so awesome. So we saw three cases, but this is just for a point load applied on a body. So for strain energy methods, or energy methods in general, so you can calculate the strain energy due to point loads, as we have done. You can do it as shear stress on the body, or the shear stress on the body, shear stress on the body, moment on the body, torque on the body, distributed force on the body. So there are several cases that we could look at, but in this case, we're going to restrict the whole introduction to point loads. We're going to take a look at shear stresses, and we're going to take a look at bending moments. And with bending moments is the one that's going to allow us to come up with a practical application, one of the many, of strain energy for deflection calculation. So let's see what the case of shear stresses. So I'm going to write that kind of strain stored like this, stored in a body due to shear stress. Mixing words, stress. Let me draw a figure just as a guide for what relations we're going to obtain here for A. So let's imagine that we have some sort of cube like this. And the cube is fixed to the ground in the bottom here. And we apply a tangential force to the top of the body, which is going to create a shear stress on the body. Because what this is going to do, but before showing what this is going to do, let me put some dimensions here. So we have, this is the height of the body. So we have also the length of the body. I'll just call it like this. Let's imagine that this body also has certain depth here, like this, but I don't want to fully draw it. Something like this. And we apply this shear force at this body, which section is represented by the rectangles A, B, C, and D. So as soon as I apply this, so there exists certain deformation of the body that is going to happen in which color? Maybe in red. It's going to happen like this. So we're going to have this, so it's going to deform. Let's exaggerate the deformation, yeah, like this. So it deforms like this. It comes from here to here, then comes back to here. And then I can try to draw. So it's just kind of, it deforms all of this. Something like this. So this is the move. Doesn't make sense, this part here. Yeah. We went too far. So, no, because if this is 2, this is 2. Something like this. Yeah. So the shear deformation is represented by this angle here. Phi, and this one here, phi angle. And when I apply this load, this upper part went, for example, at this point went from D to D1, or from C to C1. Now let's see what's the relationship that we can get from all of this. So we know that the shear stress equals to the tau. Again, keep using the key. Force divided by the area. But who's the area? So we could call that the depth of this body is like this, and then this is B. Then the area would be B times L. So shear stress equals to the force divided by L times B. Now, if I want to isolate the force, because we have done it because we did the force for work purposes, then I could say that, well, this equals to shear stress LB. Now, what's the shear strain? How is it defined? Well, the shear strain is defined by this angle. It's not a length, but now in this case is an angular deviation, an angle. So phi. And then if I use the small angle, let's say condition, then I could say that the shear strain equals to what? Well, let's take this area here. So if this segment, yeah, here, well, this angle equals to what? To this segment divided by this one here. So basically, so it's going to be, because those are the known values. So is the CC1 divided by CB. But we know what is CC1. Well, we don't know what is CC1, but we know what is CB. We know that CB equals to H. Now, if the load is gradually applied, is applied gradually, the load is applied gradually, then we know that the work done by the load is going to be represented by an average force, basically, again, P, which is this one here. And then work equals to force times distance. Then the work done, as defined here with these elements we have just found, is going to be the load, F divided by 2, times the distance, but the distance is how much it was extended, and this much was extended in the linear, say, direction, and a linear direction here, so it's going to be CC1. But again, I already know how much are these topics, well, these other elements here, so I can substitute this by the force. The force I know that is shear stress LB times CC1, but CC1 I can subtract it from here, knowing that CB is H. So that's going to be equal to H times phi. Now, if I introduce another topic here, another term here, that the relationship that exists between the strain, the shear strain, and the shear stress is S, being this, you can find it as G also. This is the shear modulus. Then we can keep, simplifying this equation to find something that is useful for us, which is at the end the strain energy stored due to the shear stress. So let's see here. So from the top here, I know that these 3 times LB and H, that multiplication basically is the volume of the body in here. And what else? Yeah, we could say that. So actually, I should change this already with this. Now also considering that, let's say U, let's call it shear stress, equals to what? 2, 1/2 of what? Of shear stress times the volume. But then we have phi here, and this can be related to the shear stress using the shear modulus here. So I can factor this into this equation, and in the end, I'm going to end up with this equation here, S square here. So every load type, like point load, shear force, torque, bending moment, or any other combination, can be used to find out how much is the strain energy stored in the body, in this case. It was pretty simple. Now let's look at the strain energy due to the moment, bending moment. Here. Like this term, energy due to bending moment. Like this. All right. Let's bring again our formula for the strain energy stored in the body. The total strain energy stored in the body is this one. Actually, let's bring the proof resilience, this one here. As we have written down in here, proof resilience, this one here. Actually, this can be actually the, we don't need to use the proof resilience, so the resilience only. Okay, let's draw a case. So what about if I have a beam like this? This beam is in cantilever, meaning this one end fixed. Then this beam has a length L, and there is a moment applied to the beam, a bending moment here. Great. Now, one small change we're going to do here is that we're going to say that strain energy in the body, well, is this, but let's say that it's going to depend on the volume of the body. And if that's the case, so I need to make something like trying to determine the energy in the body due to certain geometrical conditions of the body. For example, in this case, the volume. So if the volume changes, then the stored energy is going to change. So I could say that strain energy could be also represented as the integral of this U, the total strain energy, or the resilience, when I just, let me write it down like this, to separate terms, dV. Yeah, we get to know that. Now, why this change is important here is because now, for example, I know that in a bending moment, or a bending moment can be defined as the bending stress can be defined as the bending moment divided by I, the second moment of area or moment of inertia, times Y, which Y is the distance from the neutral axis to the, if we're talking about the maximum stress, we're talking then about the distance from the neutral axis to the farthest away point, so where we want to calculate that bending stress. So if I substitute this one here, so I could say, and then the strain energy equals to this one here, and then the bending stress. Just fix a little bit this, and this is square dV. Now, if I consider that the Young modulus is constant as it is the bending moment, inertia, then I could say that strain energy is going to be equal to 1 divided by 2 E m square divided by I square. So I could put it like this. And then what is remaining, which is the Y and the volume, I could represent it as the volume. It could be represented like differential of area times differential of length. Okay? And meaning that I could then split this integral into two parts and say, okay, well, this is going to be equal to this times the integral to this, which is the same as we had before. But what I'm going to say here is that the length goes from 0 to L, as is represented here. But interesting to know is that here is a term that we already know. This is the second moment of area, also aka the moment of inertia. Then we could say here that strain energy due to bending moment equals to what? Well, to 1 divided by 2 times the Young modulus, then times what? This is I, m square, L if I just integrate this dx from 0 to L, divided by just 1I, because 1I here cancels out with 1I here. And this ends up being the strain energy due to bending moment. Great. Now we're coming to the application part of everything that we have seen so far. Well, all of this, it could be applied, because with all these equations, as you're going to see in the practice session, you can find deformations for certain cases. And it's going to be very interesting to see how they developed in a way that we are not used to apply these equations before, for sure, because we've used different methods to calculate deflations. But now we have another tool in our tool set. So let's see. Now, one of the, let's say, key parts that where everything, say, focus or concentrates in here is what is called the Castigliano's theorem, the first theorem. Let me write it down here. Castigliano's first theorem. And we're going to first derive it, and then we're going to mention why it is important, why Castigliano's first theorem should be kept in mind if we work all the time with strain, stress, and elasticity problems in this case. All right, so to start working with Castigliano's first theorem, we're going to imagine that we have a body, a beam, for example, like this. I'm going to draw a beam in here. And then we are going to apply forces at certain points of that beam, something like this. Doesn't have to be kind of exactly space or something like that, no. They're just forces applied. So we have force 1, we have force 2, force 3, and force n, meaning that we can have n number of forces there. So when we apply those forces, this body is going to deform according to those forces. So it means that there's going to be in the direction along this force, there's going to be a deformation. That is not the deformation due to the force, but is the deformation in the position or in the line of action of the force, and we're going to call it this one delta 1. So the same is going to happen with the second force here. This is going to be 2, then another one in the line of action of force 3. So it's something that you can measure there at the 3, and then definitely something in here, very small but existing at the n. Yeah. So wherever you apply the force on the body, you can measure how much is the displacement or the deflection on the body. So we can call this like deflection curve, like this. Now we're going to assume that these forces are gradually or applied gradually. Yeah? So forces are applied gradually, and we're going to call them Fi for any force with I varying from 1 to 3. It should be a 3 up to n. Then we have the deflection, as I mentioned already, along the direction of the forces. We're going to call it delta I, with I also varying from 1, 2, 3 up to n. Now, how much is the total work? Well, we know that work is equal to force times distance. Yeah. But now we have many forces, and we're measuring many distances corresponding to this, well, not corresponding to these forces, but in the direction of those forces. Then we could say that the total work is the sum of the work done by all of the forces. And we can call it like this. So total work equals to the sum, and we are going to go from I equal 1 to n, because we have n forces, of what? Of the definition of work, which is Fi, then the variation of the displacement. Okay. Now, as energy is conserved, meaning that there is nothing else acting there, so we say that bring that like this, that work equals strain energy, meaning that, well, just for redundancy purposes, I could say that strain energy equals to the sum of these forces, or the work done by these forces. Perfect. But now, if we know that let's assume, let's bring down the gradually applied condition. So the gradually applied condition says, I'm going to write down here, gradually says that applied to these cases of many forces, well, we don't use actually the whole force, but we use an average of the force, which is going to translate to this. Yeah? And then again, Fi times delta sigma I. Awesome. Now, this is where the interesting thing starts happening. So let's imagine that we are going to just look at this point here, where force 1 is applied. Yeah? So if I take that force 1 and I increase it by an infinitesimal amount, delta F1, while keeping the other forces the same, meaning they don't change in magnitude. Yeah? Then I could say that, well, if I take this force, increase it by an infinitesimal amount, delta F1, then what is going to happen is that definitely sigma 1 is going to increase by an infinitesimal amount, delta sigma 1. So the additional work done to increase the load will cause an infinitesimal change in the strain energy, meaning that by increasing a little bit that force 1, what's going to happen is that I'm going to have a little bit more of strain energy created because of that. So how would that be if I draw a diagram? So for example, let me bring this diagram here. Or yeah, let's work with this diagram here and modify it. So I have this. Let me delete a few things. So for example, faster delete like this. So let me delete all of this. Let me well, it was not much bad. Let me change this. So let's imagine that we first had this work done by F1 at the beginning before increasing it infinitesimally. So let me draw back again. So we have this one here. So I can delete this. Well, I didn't save that much. So here initially is what we have. So here we have force 1, and here we have the displacement at the point, the 1. So what about then, as we are suggesting, we increase a little bit more here. So this would be F1 plus a differential infinitesimal amount of that force. Let me write better. Then what's going to happen is that this is going to increase, let me use this one here, a little bit of strain energy. Then I can bring this line down. Then we mentioned also that, well, now this point here is going to be what? Well, it's going to be the initial extension I had plus the variation of that extension, infinitesimal variation of the extension due to the increased work. Yeah. So this one here is the extra work done by that infinitesimal amount. So that is, this one here is delta U. Yeah. But how much is that delta U? Well, yeah, well, there's a way to calculate it. So I could divide this into two areas to, just to be easy to manipulate. So this one here, so I could say that this area here, the work due to this rectangle here is going to be just F1 times what? Well, times just the small variation here, which is delta differential of delta 1. Yeah. I keep calling it delta. Is it delta? I just have mixed up the symbols. Let me see. Maybe I've been calling it wrong. No, it's delta. Yeah, that's correct, delta. But then how much is this small piece here? This one here, this one here, and this one here. Well, this small piece here, how much is that work? Well, let's see. That small part there is just going to be kind of the area of this rectangle where the base is just delta, differential of delta, the extension, differential of the extension, 0.1, and the differential of the force there. So it's going to be 1/2 differential of the force times differential of the extension here. Then the extra work done by that increase, that we took just one force and increased it a little bit, is going to be what? Well, it's going to be 1/2 of this one here, like this one here, times that, plus the area of the rectangle there, sigma 1. Then I could just try to take common terms and then say that, well, this is equal to 1/2 of the differential or the increase of the force plus the force times the increase, differential increase, or infinitesimal increase of the extension, like that. So this is what's happening in, actually let me mark it here, the extra work, as seen in point 1. But then what's the extra work when I increase force 1 by an infinitesimal amount, but looked from the other forces? Yeah. So if I bring back another diagram like this, so I have again the load, I have here the extension, then I have the initial work that was done by the forces at other locations, because we're talking about other locations, at other locations. Then we have here the force applied, in general force, because it could be force 2, it could be force 3, 4, or force n. But then what happened was that when I increased, and this is just an extension of value, when I increased the force 1 by an infinitesimal amount, then there is a consequence replicated in those other positions that I'm monitoring. And how did they feel that change? Well, for them, it was basically that at that point, they didn't change any force, but what they saw was that there was a change in the extension, or in the strain, to sigma plus sigma, or delta sigma. So this was what they saw. Look at the difference. This is what point 1 saw when we increased infinitesimally force 1. This is what the other forces saw when we increased force 1. So the work done is the area under this rectangle, or the area of this rectangle, and this is going to be just what is going to be F times the differential on the extension. Awesome. Then we could write it down, let me see here, that for example, in any other cases, in other locations, then the differential of the strain energy equals to F times this one that we have just written. So we can generalize then, by seeing this case, that what happens when you increase the force in one side, and then what happens with the rest, generalization. We could say that the total work equals to what? Well, equals to, what is it? Let's start with this one actually, is that if I have n minus 1 forces, because I'm not counting force 1, but I have n minus 1 forces, then is the work done by those n minus 1 forces. And that's going to be equal to the sum from I equal to 2 now, not from 1, from 2 of Fi delta, the differential of extension I, plus the variation. Sorry, this is generalization. This is the amount of extra energy that was created or was developed by increasing infinitesimally force 1. So it's going to be, okay, we mentioned already, so it is the differential of work that appears in the other forces that I didn't touch, and then plus the force that I'm touching, the differential of energy that of the force I'm touching, which is this one, and I can write it down as this one here, so this one here. Awesome. Okay. So let's see what we have here. Perfect. Now, if all the forces then are applied gradually from 0, yeah, then that, how to call it, that amount of energy that it was generated, well, is there not that all loads are gradually applied from 0, but what about if all loads are gradually growing now? So not just in this case. So the case that is just that's 1. So but we could say that we have a relation for the energy, and we have a relation for that increase in energy due to the changes on the loading. So if that's the case, then now that we're looking at all forces are being increased at some point, so this is going to be equal to 1/2 of what we have here, it's kind of this, what is it? Yeah. Force 1 plus what I increased, yeah, times the extension I had, plus the increase on the extension, plus now what other forces are, say, experiencing extension, I plus the differential of extension. And if I start, say, separating these terms here from this equation and try to simplify whatever is left from them, so let's see, we're going to end up with this, so just bear with me. So we're going to have this one half of F1 delta 1 plus 1/2 of F1 delta sigma 1 plus 1/2 of delta F1 times sigma 1 plus 1/2 of delta F1 delta sigma 1. And then plus this, I could split that sum into two parts. It's going to be like this, to n of Fi, sorry, differential, this one here. Awesome. Then I could collect some terms here. And then, for example, I know that, you see that how this one here, sorry, this is applied gradually. And if this is applied gradually, then this has a half here, and then this has a half here, and a half here. Sorry about that, just missed it. And then I see how this term here is pretty similar to this term here, so I could collect them and say, well, you know what, now we're going to have 1/2 of the sum from I equal 1 to n of all of that. So I could collect them like this. Then I could bring this one here and say, well, plus 1/2 of the sum of all these terms here. But wait a second, so I have this term here, f multiplied by the differential of the extension. I have this term here, I have this term here, so I could call it I equal 1 to n fi differential of extension, like this. I could say, you know what, a multiplication of two differentials for our case here is too small, so let's just get rid of that, and meaning that the only term alive is going to be this, force 1 times this one here. Great. Now, what else? Well, we know that this term here is actually U, strain energy. So we should have it like in here. So that's the strain energy, U. So it means that this is equal to U plus this sum here, I equals 1 to the power of n Fi to I, plus this other term here, 1/2 of, let me write it better, F1, this one here, which means that du, if all of this is du, so the increment in the strain energy, so I could just take this 2, put it in the other side, and say that, well, now that 2 du equals to what? To this sum here, which is 1 of Fi plus the F1. Nice. Great. So we have that, but we have a couple of terms of what that incremental work means. Meaning, we have this one here. So this is the one that we have written. But we also know that this du could be represented as, where is it? I'm trying to look for it. This one here. This one. Should have marked it before. This generalization. So if that's the case, I could do then subtract this, I equal 1, and Fi times the derivative of this one here, plus this term here, minus the generalization of that term over there, and that's going to be minus this one here, I equal 2 to n Fi sigma I, so this one here, minus this term here, so it's going to be 1/2 this one here. Now I can expand this. Let's see how to see. So let's see. So I have this one here And it is convenient to then to extract this parenthesis here to see the terms that are kind of in a cleaner way. So let's do it. Plus this one here. This is 1 minus this one here. Minus, let's see, this one times this. So it's going to be 1/2 df1, the differential of the extension, minus f1 times the differential of the extension. And if you see this term here and here, this can form right away the sum of this product here. And if they form this product, which happens to be negative because both terms are negative, then it means that I could cancel out this one and this one because they're the same. Also, I could say, you know what, this is something that is very small, these two terms, so I can cancel those two terms. And then in the end, I could say that then that the increase in the strain energy of the system depends only on this term here. Remember that we increased that value of that force, yeah? Which, if I rearrange a little bit differently, then it's going to end up being something like this. So we have a relationship between the energy and, let's call it, deformation. So this says, this is something like, for example, that what all this represents is that the partial derivative of strain energy with respect to this force here gives the deflection of the load, or gives the deflection of the body in the direction of that load. Meaning, if I get these such relations where I know what's the increase in the total strain energy of the system, and I know how much was the increase on the force, then I get to know how much is the deflection in that point where the force was incremented. We can do that for any other loads, and it's going to say the same. And that's what's kind of what it states the Castigliano's theorem in this case, is that, for example, we could say that the rate of change of strain energy, because this is the rate of change of strain energy with respect to an individual applied load, just one load, yeah, then it gives the deflection in that position or along the direction of that load. That's what is said in that sense. Yeah. So where is the application here? So let's take one of the many applications of the Castigliano's theory in this case, and then we could call it application to beams. Application to beams. And what it says, well, we know that beams subjected to bending moment are going to be, not ruled, but we need to use such approach here, like some abstract like this. So I could write it down, like in this case, like u equal to, let's put everything inside of the integral m square divided by 2ai. Remember that there's just one I left here, and then dx. Yeah, and that this was varying from 0 to L. So let's bring this one here. Perfect. And then if this is the strain energy, and I differentiate the strain energy with respect to the load, meaning if I differentiate this, partial differentiate because, and it's partial differentiate because now we get to choose which load we are going to be studying. So that's why it's a partial derivative here. So like this. Again, this should be force. Then, well, it's just differentiating this, what we have here. So it's the differential of this with respect to the force of the integral of what we have there, and 2 like this. Perfect. Now we're going to continue considering that Young modulus and the inertia is constant, but be careful because you can be working with elements, bodies that change in shape at some point of the geometry, and that would induce a change in the inertia properties on that section. So you need to consider that in the future. We're not going to do it here, but just be careful about that. So if I partially differentiate this with respect to f, then we can consider that the moment, more specifically, bending moment, change in function of f. This moment is function of f in here. So I need to differentiate this part here with respect to f. So we would say that then, if this is equal to the deflection here, then the integral from 0 to L, if I put this partial differential 2 in the insides and I take the derivative of m with respect to f, then it's going to need to apply some chain rule. So it's going to be, where is it? It's going to be 2 times m times the partial derivative of m with respect to the force, which I don't know what it is. And then this is going to be the x divided by 2ai. But we could then cancel out these 2's, and then in the end we're going to have that whenever we find a case of determining the deflection at certain points of a beam due to the bending moment using strain energy concept, then we could apply such theorems such as the Castigliano's theorem to determine that deflection. So this is going to end up being like this, and then this one here, the x, and then we could put here 1 divided by ei. And this is what Castigliano's theorem says. Pretty interesting, the concept of this. And why is this important for us? Well, one of the things is that Castigliano's theorem is very flexible, meaning that it could be applied to linear and nonlinear material. So in this case, we're talking about a specific condition, but it's pretty flexible. It could be applied to determinate or indeterminate structures. When we talk about determinate structures, are those structures which a number of constraints are equal enough or are enough to maintain the static condition of the body of structure or element. And when we talk about indeterminate structures, or we are talking about structures that have way more constraints that they need to maintain the static conditions of it. We could, well, what is being done, for example, with Castigliano's theorem is that it is being used to optimize structures to ensure that the deflections or displacements are within acceptable limits. So this is very applied to displacement analysis or elasticity related to displacement or elasticity analysis, where you are way more interested in how things deform than how things will, let's say, stressed. But even though you're just taking a look at deformation at certain points, you are not missing the point on how the stresses are developing there. Yeah. Well, what else could be said about the Castigliano's theorem is that it can solve very complex problems where multitude of loadings are applied to a body with specific or particular geometries that are not, let's say, very common. So we could use Castigliano's theorem to determine the displacement of the structure or certain parts of the deflections of certain parts of the structure at that point. And yes, this is pretty theoretical. I understand, a little bit boring. I have to accept it. It is important that a concept that from, I would say, let me try to remember in this case that, I hope that, well, I didn't find it here, but Castigliano's theorem is the 1800s and something, where he wrote a book on elastic deformation, basically. And that's something that, close to, well, soon it's going to be 200 years old concept, and we're still using it. Those are things. And that's the thing that amazes me the most, is that the very old concepts are pretty much valid still today. And we need to acknowledge that they're pretty cool. So yes. Yeah. Theory, Elastic Stresses in Structure was a book written by Castigliano, where he proposed all these methods. Well, let's finish the lecture now, and where you're going to have practice sessions where the practical part of this is going to be shown, and you're going to be given the opportunity to match all these sort of abstract equations into practical problems where you could take these equations and solve real-world problems. Thank you very much for being with me until now, and see you in the next lecture.